Continuing on here, we are moving on to derivatives. So now we're kind of getting into some of the bigger topics in calculus. Just doing an intro. We're not going to do anything complicated like the chain rule um, or L'Hopital's rule or anything like that. We're not going to go deep into a lot of the derivative stuff. We're just going to be looking at kind of the basic derivative, where it comes from, and how to do some simple ones. We're not going to do a quotient or a product rule or anything like that in this one. So again, it's just an intro. So let's say I have these functions, and the first question that I want to ask is, what is the slope of each one? So y equals x, what's the slope? Right, it would be 1. What's the slope of the second one? It would end up being 2, and the slope of the last one would be -3. So if I'm asking for what's the slope of each one, I end up you can just tell me what it is because it's just written in front, okay? It's the m value of these linear functions. And so what you see written here is what we would call y prime, okay? So y prime 1, y prime 2, and y prime -3 is what we would have. So if you see those little apostrophes, that means y prime, okay? Going back to geometry, actually, when we talk about images and pre-images, the image is always going to be the prime of the pre-image. So just that. So let's say we have this line, and we want to write the equation of this line. So if we write the equation of this line, we end up with y equals -3/2x plus 1/2. Okay, so now take a second and find the difference quotient of this. And when you found the difference quotient of it, take that limit and approach it as h approaches 0. Okay, so like what we did in the last video, take the difference quotient and then apply the limit as h approaches 0 to it. Okay, so when you did this, you should have gotten a -3/2. And so that's what we got as our difference quotient. So now what is the slope of this line? The slope of this line is -3/2. And so as you see, the slope of a line is found by using the difference quotient and applying the limit as x approaches 0 to it. And so with that, we end up being able to find our slope of that line. And it's not just for lines, it's for any function. So any function that you can find the slope for, you can find the slope of. Okay, and so this one ends up being a straight line. It's fairly straightforward. Well, now the next question would be, what if you had some sort of curve? Okay, so like here we have a parabola. So parabola y equals x squared, very straightforward. And so if we want to find the slope at 1, one way we can do it is we can take our points from one to another one and then keep it smaller and smaller and smaller. So we'll find the slope from 1 to 3, 1 to 2, 1 to 1.5, and 1 to 1.1. Okay, so if we go 1 to 3 of this, what we end up doing is that we have an h value of 2. Remember, the h is the difference between each point. So the difference from 1 to 3 is 2. So that means we do the f of, this is basically the f of 3, minus the f of 1 divided by 2, which is just your slope formula. Change in y over the change in x equals the slope. And so the change in y would be your f of 3 minus your f of 1. Your change in y, or your change in x, would be 3 minus 1, which is your h value, which is 2. So we end up with f of 3 minus f of 1. F of 3 is 9, f of 1 is 1, 9 minus 1 is 8, 8 over 2 is 4. So that means the slope from 1 to 3 is 4. Now, do you think that's the slope at 1? No, it's a little far away. So let's go a little closer. So 1 to 2. 1 to 2, our h value is now 1, because it's only a difference of 1. So that would be this green line that we have here. When we plug in a h of 1, we would go f of 2 minus f of 1 all over 2, or all over 1. So this ends up being f of 2 minus f of 1, which again is just, it's asking for the slope from 1 to 2. So we got 4 minus 1 all over 1, which is 3. So our slope is 3. So you see now we're a little bit closer. We went from 4 down to 3. Okay, but is that close enough? No, we could probably get closer. So now we can go to 1/2. So now our h value is 0.5. So now our h value is going to be in decimals. So then we do our f of 1.5 minus the f of 1. So 1.5 squared is 2.25, minus 1 is 1.25 divided by 1/2 gets you 2.5. So now our slope there would be 2.5. Now, do you think that's it? Well, we can probably get a little closer. So the last one we're going to go is 0.1. So when we plug in a 0.1, we'd have f of 1.1 minus f of 1 all over 0.1. And we would go through solve it. 1.1 squared is 1.21 minus 1 all over 0.1 gets us 2.1. So as you see, we got closer and closer and closer, and now we're getting closer. Now, could we do it again? Yes, we could go 1 to 1.01 to 1.001 and so on and so forth. We can get smaller and smaller and smaller. Now, if we wanted the exact slope, we'd keep going and we'd try to find that. Now, there is a quicker way, which is using what is called which is using your difference quotient and the y and the limit. So using the difference quotient, which again, limit as h approaches 0 of f of x plus h minus f of x all over h, if we plug in x squared, so if we plug in our x squared, we end up with x plus h squared, because we replace the x with x plus h, minus x squared. X plus h squared, again, we talked about previously, is x squared plus 2xh plus h squared minus x squared. The x squareds cancel, the h's reduce, leaving us with 2x plus h. Now we take the limit as h approaches 0 of this function, which gives us just our answer as 2x. Now, that means that the slope for y equals 2, or x squared, is y prime equals 2x. So what that means is that instead of finding the slope for a single point, we have found an equation to find the slope of the line at all points. So, if we wanted to find the slope at, let's say 3 in this case, if we wanted to find the slope of this parabola at x equals 3, so it's going to be y equals 9, at that point, what is the slope? We end up plugging in a 3. So we plug in a 3, we end up with a 6. So the slope at 3 is approximately 6. And then if we plug in 10, we can find the slope at 10 using the same equation, which gets us 20. Okay. Now we can do the same thing with negative. So if I want to find, okay, what's the slope at x equals negative 2? So x equals negative 2, I plug in negative 2 into this equation, I get a negative 4. Well, that makes sense because if I were to draw a tangent at negative 2, it would be going down. Okay. Now, in this formula, where is the vertex? So where's the turning point of this? The turning point of it is located at 0. Okay. So the turning point is located at 0, right here. Well, if I draw a tangent line at 0, what's my slope? My slope is horizontal, which means the slope is 0. If I plug a 0 into this equation, I get a 0. Okay, so the derivatives, or this y prime derivative, is helpful for us to find where the turning points are of different curves, because we're able to find where the slope is 0. Okay. All right, so now there is a trick to do these, what we're basically going to call them derivatives now. There's a trick of doing these derivatives faster without having to do the difference quotient all the time. And now that you know this trick, you can use this trick. So given a simple function, basically a polynomial, what we want to do is we want to look at the coefficients and we want to look at the exponents of them. Okay, so I have it simplified down, so it's just the 3x squared plus 5x minus 8x to the 0, which would end up not having a variable there. But what we want to look at is the exponents and the coefficients. And what we're going to do is we're going to drop the power and multiply it by whatever the coefficient is. So you drop the power and you multiply it. So the first one would end up being 3 times 2. Next one would be 5 times 1. Last one would be 8 times 0. Okay. And when we do that, what ends up happening is that we subtract, or you can think of just get rid of, our exponents. So the exponents fall by 1 also. So if we drop the 2, okay, the exponent goes from 2 to 1. If we drop the 1, the exponent goes 1 to 0. If it's 0, then it ends up canceling out. So now we have 2x 2 times 3x, and then 1 times 5, and then 8 times 0. The new exponent is always going to be 1 less than what it originally had. So if it had 1, it goes down to 0. If it had 3, it goes down to 2. If it had 12, it goes down to 11. Okay, and that brings us to our final answer, which is the y prime is equal to 6x plus 5. And that is, if we took the difference quotient, applied a limit as h approaches 0 to it, that is what we would get. And as you see, this took me 1/10 of the time that it would take me to do the difference quotient all the way through. And so that's why this is this little shortcut that we can use. So let's find the derivative of the first one. So the first one, what we're going to do is we take the powers and we drop them and we multiply them by the number in front. This would be a 1, obviously, and the last one ends up as 0. Now, one thing with constants, so numbers that don't have x's, they just disappear. Okay, so numbers that don't have x's just end up disappearing. Okay, so here we'd go 4 times 5, 20, 3 times 6, 18, 8 times 1, 8. So our coefficients are going to end up being 20, 18, and then negative 8. And now the variables are going to be x to the 4th, x to the 2nd, and then no x. And that's our derivative. Okay. So now if I wanted to find the slope of this line at any x value, all I would have to do is plug in that x value into that bottom one. So if I wanted to find what's the slope at 0, when x is 0, what's the slope? It ends up being negative 8 because I plug a 0 into the x's, getting me an answer of negative 8. If I wanted to know what's it at 1, it'd end up being, what's that, 30. Okay. All right, so now take a second, do it with the second one. Try to find the derivative of it. All right, so the derivative of the second one ends up being 100x to the 9th minus 64x to the 7th plus 36x to the 5th minus 16x to the 3rd. So as you see, you can take you just drop the powers, multiply it by the coefficients, and then subtract the coefficients by 1, and that is the derivative. So the slope of that curve at any point is the one that's below it. Okay, so now the bottom one, you see, we don't have our x values. We have an x in the bottom of it instead of the top. And so what we have to do is we have to do a little bit of a change, not much though. The derivative of this one ends up being y equals a negative 1/2 x squared. Now the reason for that is because if we took the 1 over x and we wrote it with an exponent, so what would the power be for this? It would be x to what power? It would be x to the negative first power. So since it's x to the negative first power, now all we do is we do the same thing. We drop the power, subtract it by 1. So we drop the negative 1, subtract it by 1, gets us negative 2. So we have negative x to the negative second power. Ends up being our new equation, which then if we don't want the negative exponents, gets us ours. So if you have numbers, if you have variables in the denominator, what you can do is you can move them to the top. Okay, and the ones that we're going to see, basic ones, you'll see like 1 over x to the 5th, something like that. You just change it to x to the negative power for them. All right. All right, last one here. So we have y equals x to the square root, or y equals the square root of x. And again, we want to use our power rule. So what is the power of square root of x? So what's the exponent of it? The exponent would end up being 1/2. Okay, so it end up being 1/2, so we can rewrite it as y equals x to the 1/2 power. Okay. And now we just use our power rule again. Take the exponent, drop it in front, subtract it by 1. So we drop the 1/2 in front, so we're going to be left with 1/2 x. And then our power is going to end up being 1/2 minus 1/2, which is minus 1, which gets us a negative 1/2. And so now if we attach that power to the exponent, it's a negative exponent, dropping it to the bottom. X to the 1/2 power is a square root. And so it's written like this. Okay. These, if you have square roots in the denominator, you can keep the square roots in the denominator. That's fine. It's not a big deal. But that would end up being your derivative. If you wanted to radicalize it, it would end up being, what is it? Square root of x over 2x, something like that. So, all right. Okay. So that's the end of that section. That's our derivatives using our power rule. Now there's many other rules for derivatives that you can use, but this is just your basic one. This is kind of the first one you have.